Alright guys, in this video I'm going to go through everything that you need to memorize for A-level physical chemistry. Now before we get started, make sure you like, comment and subscribe, and make sure you check out some of my other videos. So the first chapter of A-level physical chemistry is thermodynamics, and to begin with you want to make sure that you know all your definitions. So the enthalpy change of atomization is the enthalpy change when 1 mole of gaseous atoms is formed from its element in its standard state. So for example, for sodium it would be sodium solid turns into sodium gas, and then for oxygen, well, oxygen's standard state is already a gas, however it exists as O2. So to balance this equation we're going to have to add a half at the start here. So next we have the bond dissociation enthalpy, and this is the enthalpy change when 1 mole of a covalent bond is broken into 2 gaseous atoms. So for chlorine this would be Cl2 turns into 2Cl, and you want to make sure that you write it into the gaseous state. Next we have the first electron affinity. This is the enthalpy change that occurs when 1 mole of gaseous atoms gain 1 mole of electrons to form 1 mole of gaseous -1 ions. So for example, for oxygen, you'd have oxygen in the gaseous state, and you're adding an electron. Then we have the second electron affinity. This is the enthalpy change when 1 mole of gaseous -1 ions gain 1 mole of electrons to form 1 mole of gaseous -2 ions. So for example, for oxygen you get O- in the gaseous state and an electron, and that forms O2-. And then we have the enthalpy of lattice formation. This is the enthalpy change when 1 mole of an ionic crystal lattice is formed from its constituent ions in the gaseous state. So for example, for sodium chloride we have Na+ in the gaseous state and Cl- also in the gaseous state. The opposite of lattice formation is lattice dissociation. So if we go up here, we have the formal definition of lattice dissociation, which is the enthalpy change when 1 mole of an ionic crystal lattice is separated into its constituent ions in the gaseous state. So for example, for sodium chloride it would be sodium chloride solid turns into sodium plus in the gaseous state and Cl- in the gaseous state. Okay, so we can use all of these definitions to work out a certain enthalpy using a Born-Haber cycle. So for example, here we have the enthalpy of atomization of magnesium, so that's 150, and that would go over here. And then the first ionization energy of magnesium is 738. And the second ionization energy is 1451. And then the atomization of Cl is 121. However, we're going from Cl2 to 2Cl, so because of that we're going to have to times it by 2. And then the electron affinity of chlorine is -349. However, once again we've got 2Cl to 2Cl-, so you want to times it by 2. And then the lattice enthalpy of magnesium chloride is unknown, it's what we're trying to work out. So for now I can just call that something like X. And then the enthalpy of formation of magnesium chloride is -641. Right, so we can use Hess's law that says the enthalpy change is independent of the route taken to work out x. So what we can say is, if I go this way, that's also equal to going straight from here to here. So by doing that, I get and then I get that x is equal to minus 2524. So as you increase the sizes of the ions, the lattice enthalpies decrease. Whereas if you increase the charges of the ions, the lattice enthalpies increase. So for a perfect ionic model, which is 100% ionic, the theoretical and the Born-Haber lattice enthalpies will be equal. Now covalent character occurs when the positive ion is small and the negative ion is large, and the ions have multiple charges. For ionic compounds with covalent character, the charge cloud is distorted. This means that the theoretical and experimental Born-Haber lattice enthalpies will differ. Entropy is a measure of how much disorder a substance has. This means that a gas is going to have a higher entropy than a liquid, and a liquid is going to have a higher entropy than a solid. Because if you think about it, in a gas, the particles are like further away than a liquid, and then for a liquid, the particles are further away than a solid. The units for entropy are joules per Kelvin per mole. The formula for entropy change is the sum of the entropy of the products minus the sum of the entropy for the reactants. There will be a significant entropy change if there's a change of states from solids or liquids to gas, or if there is an increase in the number of moles from reactants to products. Now the formula for the change in Gibbs free energy is the enthalpy change minus the temperature times the change in entropy. The units for these are, well, Gibbs free energy is in kilojoules per mole, and so is enthalpy. And then the temperature is in Kelvin, and the entropy is in kilojoules per mole per Kelvin. So one thing to make sure of is that when you work out entropy change, most of the time it's going to be in joules per Kelvin per mole, like we did here. So to convert it into kilojoules per mole per Kelvin, we need to divide it by 1000. Now if the Gibbs free energy is less than 0, the reaction is feasible. And when Gibbs free energy is equal to 0, that's when the reaction becomes feasible. So if we plot a graph of Gibbs free energy versus temperature, we get that the gradient is equal to minus the change in entropy, and the y-intercept is equal to the enthalpy change, and the x-intercept is the temperature when Gibbs free energy is equal to 0, so the point at which it becomes feasible. Now the enthalpy of hydration is the enthalpy change when 1 mole of gaseous ions become aqueous ions. So the reaction for this is the gaseous ion, and you could just add AQ, and then the ion becomes aqueous. And then the enthalpy of solution is the enthalpy change when 1 mole of an ionic solid dissolves in a large enough amount of water to ensure that all of the solid has dissolved. So for these types of questions, I like using Hess's law. So we know that we start off with KCl, and we're forming K plus aqueous and Cl minus, and we want to work out this enthalpy change. And next I'm going to write down K plus and Cl minus in the gaseous state. And what I know I can get from here to here by dissociation, which is 701 plus, and then I can go from here to here by saying I hydrate this ion to that, which is minus 322, and I can hydrate this ion into that, which is minus 364 joules or kilojoules. And then I can just go from here up here, which is 701 minus 322 minus 364, which equals 15 kilojoules per mole. Okay, so now we're on to rate equations. So we're going to begin this section by talking about the order of a reaction, and this is the power to which the concentration for reactant is raised in the rate equation. So to work out the orders, I've got an example here. So for A, I'm going to use experiments 1 and 2, and the concentration of A increases by a factor of 3, whereas the rate increases by a factor of 3 squared. So this power 2 here tells me that the order of A is 2. And then for B, I'm going to use experiments 2 and 3, and that's an increase of 2 for the concentration, and the rate also increases by a factor of 2, but I'm just going to write a power 1, and that power of 1 tells me that the order is 1 for B. And then for C, I'm going to use experiments 3 and 4, and the concentration doubles and the rate also doubles, so then that's going to be an order of 1 as well. So for the rate equation, my rate is equal to K A squared times B times C. Now instead of using this method, you could form a general equation for the rate and sub in your concentrations and your rates. However, this does involve a bit more advanced maths. So for example, for this experiment that we have here, we've got that the rate is equal to K X to some power that we don't know, so let's just call that power M. And then we've got Y to some power, let's just call that power N. So then we can sub in our experimental values. And then I'm going to do this for experiment 2, and I get and then lastly I'm going to sub in the values for experiment 3. And then I'm going to do equation 2 divided by equation 1, and I get and from here I get 2 equals, well, I can cancel out my k's over here, and I can cancel this bit out with this, so I get which is equal to 2 to the power of m. So that means that m is equal to 1. And then I can do equation 3 divided by equation 2, and I get that 8 is equal to, well, I can cancel out these k's here, and we already know that m is equal to 1, so 0.2 divided by 0.1 is 2, and we get And I got this here from this and using my power rules. And then we get, so n is equal to 2. So finally my rate equation is k times x to the power of 1 times y squared. Now alternatively I could have used the other method, so I can say that the increase from 1 to 2 for x is times 2, and the rate increases by times 2 as well, or times 2 to the power of 1, so the order of x is 1. Then from 2 to 3 the concentration of x changes by 2 and the concentration of y changes by 2 and the rate changes by 2 to the power of 3. Now this is why it's a little bit harder, because this rate would have been affected by the change in x as well and y. So the way we can find out what the effect of y is we can break this into 2 to the power of 1 times 2 to the power of 2, and well, we know that the 1 is because of this x here, so then this square over here must be because of the y, so the order of y is 2. So just like before, we get that the order of x is 1 and the order of y is 2, just like how we did algebraically over here. So generally the order of a reactant for AQA can be 0, 1 or 2. The overall order is equal to the sum of the individual orders. K is called the rate constant. Now if we let x equals 1 minus the overall order, then the units of K will be moles per decimeter cubed, all to the power of x per second. Now when the temperature increases, K also increases, and this is because as we increase the temperature, the particles have more kinetic energy, so they collide more, and more of the particles have at least the activation energy. So now we have a graph of rate versus concentration, and you need to know that the horizontal line is order 0, the straight linear line is order 1, and the graph that looks a bit like a quadratic is order 2. Now the formula for K is AE to the power of minus activation energy over RT, and if we take the natural logarithm of both sides, we get that ln K is equal to ln A minus EA over RT, and the units for activation energy are in joules, and the units for temperature are in Kelvin. So if we plot a graph for this equation here, we would get something looking like this, and the gradient for this graph is minus the activation energy over R, and the units for activation energy is joules. And to work out the activation energy, we do the negative of the gradient times R divided by 1000 to get into kilojoules. Next, if we plot a graph of concentration versus time, we can work out the gradient, which is equal to the rate. So we do this by drawing a tangent like here, and if we work out the gradient of that tangent, that's the rate at that point, and the gradient is equal to the change in y divided by the change in x. To work out the initial rate, draw the tangent at t equals 0 and work out the gradient. Here we have three graphs of concentration against time. The first graph is order 0, the second graph is order 1, and the third graph is order 2. Okay, so here we have the iodine clock experiment. So for this experiment, we're going to produce iodine, and that's going to react with this ion over here, which is limiting. However, eventually you're going to run out of these ions, and when that happens, the mixture turns black, and that's because the iodine that we form here is going to react with starch, when repeating the experiment, the concentration of I minus is changed to work out the order of I minus. The rate determining step is the slowest step in a reaction. The reactants in the rate determining step are all in the rate equation. The coefficients represent the order of the reactant. So for example, here we're told that step 2 is the slowest step. So the rate equation is going to be K, X, and C. However, X is made from the reactants A and B. So we can break X down into A and B. So we get that rate is equal to K, A, B, C. And then here we're given the rate equation. We're told that the order of NO is 2. So that tells us that in the slowest step we're expecting 2 moles of NO. And the order of H2 is 1. So we're expecting 1 mole of H2. Now this here has 2 moles of NO. However, it doesn't have any H2. This step here has 1 mole of H2. We can't see any NO specifically. However, this X is made from 2 moles of NO. Therefore, we can say that step 2 includes 2 moles of NO and 1 mole of H2. Since it lines up with the rate equation, we can say that step 2 is the rate determining step. Alright, now moving on to Kp. This is similar to Kc but for gases. Partial pressure is the pressure exerted by a single gas in a mixture of gases. And the formula for partial pressure is Xi, which is the mole fraction, times the total pressure. The total pressure is equal to the sum of the individual pressures. The formula for the mole fraction is equal to the number of moles of a gas divided by the sum of all the moles of the gases. So for this question here, firstly I'm going to work out the total moles. And then I'm going to work out my mole fraction of oxygen, which is and then my partial pressure is this mole fraction times the total pressure. So for the Kp expression, we do products over reactants of the partial pressures with the molar ratios as the powers. So we'd get the partial pressure of C with the power of P and the partial pressure of D with the power of Q all over the partial pressure of A with the power of M and the partial pressure of B with the power of N. Now if we let X equal the number of moles on the right hand side minus the number of moles on the left hand side, we get that the units of Kp is Kpa to the power of X. Now for this question here I'm going to use an ice table. So I'm going to rewrite the equation. So my initial moles are 1, 3 and 0. And we're told at equilibrium 20% of the nitrogen has reacted. So we've lost minus 0.2 moles of nitrogen and we're left with 0.8. That means that minus 0.6 moles of hydrogen has reacted according to the molar ratio. And 0.4 moles of ammonia has been produced. So then we get our moles at equilibrium. Then I'm going to work out the mole fractions, which are then I'm going to work out the partial pressures, which is the mole fractions times the total pressure. And then I'm going to sub all of this into the Kp expression, which is and that gets me 0.0469. And to work out the units, I'm going to do the number of moles on the right hand side, which is 2, take away the number of moles on the left hand side, which is 4. So I get minus 2 from that. So my units are kPa to the minus 2. Now Kp is only for gaseous substances, and any other substance is ignored. So for example, for this reaction here, the Kp expression would be the partial pressure of CO2, and that's it, because this is a solid, so it's ignored, and this is a solid, so it's ignored. So for this question, I'm going to rewrite the reaction and do a nice table. So initially we have 0.4 moles of ethanoic acid and 0.4 moles of ethanol and 0 moles of our product. However, in equilibrium we have X moles of ethyl ethanoate. This means that we gained X moles of ethyl ethanoate and X moles of water due to the 1:1 mole ratio. And also that means we lost X moles of ethanol and X moles of ethanoic acid. This means that our moles at equilibrium are, and then our mole fractions are now we can't really work out partial pressures because they haven't given us the total pressure. However, since we have 2 moles on the right hand side and 2 moles on the left hand side, since the moles are equal on both sides, we can forget about the total pressures and we can just use the molar fractions instead. So by doing that we get and we can simplify this to and if we square root both sides we get and then we can solve for x algebraically and we get that x is equal to 0.278. Now the larger the value of Kp, the greater the amount of products. If Kp is small, we say that the equilibrium favors the reactants. The value Kp only changes with temperature. It doesn't change if the pressure or concentrations are altered. If temperature is increased, the reaction will shift to oppose the change and move in the backwards endothermic direction. The value of Kp gets smaller since there are now more reactants and less products. Now, if the Kp or Kc value for this reaction is x, then the Kp or Kc value for the opposite reaction is 1 over x. Okay, so now we're onto electrode potentials. A half cell consists of a metal electrode and a solution of that metal. So for example, we might have copper sulfate solution and a copper electrode, or we could have a platinum electrode and two aqueous ions, such as aqueous Fe2 plus and Fe3 plus. Now in this diagram here we have a salt bridge, and the salt bridge is typically made by filter paper soaked in potassium nitrate. It allows for the movement of ions to complete the circuit. Zinc is easier to oxidize than copper. Electrodes flow from the zinc electrode to the copper electrode. The potential difference between the two electrodes is measured using a voltmeter. The voltmeter has a high resistance to stop the current from flowing. If the voltmeter is replaced with a bulb or something else, the reaction will occur and the voltage will be zero, as the reactants are used up. So for our diagram here, our cell diagram would be, well, firstly we put the most oxidized substances in the middle. So we'd have Zn 2 plus aqueous here, and copper 2 plus aqueous. Okay, and well, this thing here is the salt bridge, and the single line represents the different states. Okay, so then here we'd have zinc solid, and on the right hand side we'd have copper solid. Okay, so that represents our electrodes. Okay, so the left half cell is the negative electrode and the right half cell is the positive electrode. And I think of this as a bit of a number line. So if we have a number line here, the right hand side is positive and the left hand side is negative. Okay, so it's kind of similar to that. If you switch the half cells with each other, the value of the electrode potential would be equal but negative, and a comma is used to separate the same state. Now the formula for the E cell is the electrode potential of the right hand side minus the electrode potential of the left hand side, or you could think of it as E positive take away E negative, and you could also think of it as E redox take away E oxidation. Now when I say positive and negative, okay, I go back to that number line. So even if both electrode potentials are positive, the one that's, more on the right hand side is more positive, okay? So that would be considered the positive one. So in this example that I have here, I've got 0.80 and 0.77. Now on a number line, 0.80 is more to the right than 0.77, so it's more positive. So this is the positive one, and this is our negative one. So if I was to draw the cell diagram for that, well, this would be on the left hand side and this would be on the right hand side. So for the left hand side, the iron, well, there's no electrode there, there's no solid, so I need to use a platinum electrode. And then I'm going to do a single line to show the separation of states. And I do Fe2 plus aqueous, and then comma because it's the same state, Fe3 plus aqueous, then a double line to show the salt bridge, then Ag plus aqueous, then a single line to show the separation of states, then Ag solid. Okay. Then to work out the E cell, I could use any one of these formulas here. So when I talk about E right hand side minus E left hand side, I'm talking about this side, take away this side. So it would be 0.80 take away 0.77. I could also use this formula, which is the positive one, take away the negative one. So once again, 0.80 take away 0.77. Or I could also think of it as E reduction, take away E oxidization. And what I mean by that is, well, firstly, one thing that you need to kind of understand is this arrow is drawn as a single head. However, in reality, it's in equilibrium. So it's more like this. And between these two reactions, the one that's more positive will favor the right hand side more, and the one that's more negative will favor the left hand side more. Okay, so in reality what's happening is this one's going more to the right hand side, this one's going more to the left hand side. So the Fe is getting oxidized to produce an electron. Okay, it's losing an electron. And the silver is gaining an electron, so it's reducing. So we do E reduction, which is the silver equation, take away the E oxidization, which is the iron reaction. So once again, 0.80 take away 0.77. And we get 0.03 volts, okay? So I wouldn't say you have to use one over the other. I'd say in different scenarios, one might be quicker to use, okay? One of these formulas. And then we're asked to write down the overall reaction. So for that, we use the fact that this reaction here is going on the right, and this reaction is going to the left. So the top reaction becomes and the bottom reaction stays the same. And then when we add them together, well, these two electrons are going to cancel out. So then we're just left with okay, and that's the overall reaction. For a reaction to occur, the E redox has to be greater than the E oxidization, and this is because the E cell has to be positive. The conditions for standard electrode potential are all solutions are at 1 moles per decimeter cubed. The temperature is 298 Kelvin, and the gases are 100 kilopascals, and there's no current flowing. Now the electrode potential of the half cells is measured by setting up a cell with the half cell and the standard hydrogen electrode. The standard hydrogen electrode is assigned a potential of 0 volts. This is the reaction that occurs at the standard hydrogen electrode, and it's always on the left hand side. The standard hydrogen electrode has the same conditions as the standard electrode potentials, as well as the platinum electrode. Alright, so sometimes you're given a list of standard electrode potentials, and you're asked to work out which one's the best oxidizing agent or the weakest reducing agent, something like that, okay? So for this, what you want to do is remember SOAP, and that is the strongest oxidizing agent is positive. Okay, so that means that the strongest oxidizing agent is somewhere here in the most positive reaction. An oxidizing agent is something that gets reduced itself, so it's going to be the F here because it's gaining an electron. So this F here is the strongest oxidizing agent, and if the reaction contains the strongest oxidizing agent, it also contains the weakest reducing agent. And if you think about reducing agents, it's something that's getting oxidized itself, so it's going that way. So the reducing agent here is the F minus. Okay, so if this whole thing is to do with positive, then the weakest oxidizing agent and the strongest reducing agent is to do with negative. So we're focusing on this one, the most negative. And once again, the oxidizing agent is on the left hand side. So the Li plus is the weakest oxidizing agent, and the Li is the strongest reducing agent. The effects on E cell made by changing conditions can be predicted using Le Chatelier's principle. Sorry, I think this is meant to say the concentration of reactants. So increasing the concentration of reactants shifts the equilibrium to the right hand side, increasing the electrode potential of the right hand side, which increases the E cell. And then if the cell is exothermic, increasing the temperature shifts equilibrium to the left hand side, and this increases the E left hand side, which as a result decreases the E cell. Cells are non-chargeable when the reactions that occur within them are non-reversible. The forward reaction occurs on discharge. Charging causes the reaction to reverse. For these reactions here, you don't need to memorize the electrode potentials, but you need to remember which one's positive and which one's negative, and then from there you can figure out the overall reaction. Fuel cells are used to generate an electrical current and do not need to be electrically recharged. Okay, so for these reactions here, once again, just remember this one's negative and this one's positive, and then you can work out the overall reaction. The advantages of fuel cells is that there's less pollution and less CO2, and also there's greater efficiency. The limitations are that it's expensive and it's dangerous to transport hydrogen. Alright, now we finally made it to the last chapter of physical chemistry, acids and bases. So an acid is a proton donor. A base is a proton acceptor. Strong acids completely dissociate, whereas weak acids partially dissociate. Whenever you see a P, that just means minus log. So for example, pH means minus log of H plus concentration. And if we want to do the opposite and work out the H plus concentration from the pH, we do 10 to the minus pH. Okay, so to work out the pHs of strong polyprotic acids, we use the fact that if the concentration of this is something like 0.5, then the concentration of the H plus would be 1 from the molar ratios. So that's how we figure out the H plus concentration. So then the pH of this would be pH equals minus log of 1. In general, we can summarize that as minus log of 2 times the concentration of the acid. Notice how this number here is the same as this number here. That would always be the case for strong acids. Next we have Kw. So the equilibrium water reaction is endothermic, and Kw is H plus concentration times OH minus concentration. Now in pure water, we assume that the concentration of water is constant and the concentration of H plus equals the concentration of OH minus. And because of this, in pure water, Kw would simplify to H plus squared. Now, since this is endothermic, if we increase the temperature, the equilibrium shifts to the right. This means that the H plus and the OH minus concentrations would increase. And so Kw would increase. And pH would decrease. Now, for strong bases, to work out the H plus concentration, we can do this where we use the molar ratio to work out the OH minus concentration. So here in this case it would be 0.46. And then we can rearrange the Kw expression to say that H plus is equal to Kw over the OH minus concentration, which in this case would be equal to Kw times 2 lots of our original base concentration. And then by working out H plus, we can work out the pH by minus logging it. Okay, so here I've got an example to try. Firstly, I'm going to write down the dissociation of barium hydroxide, which looks like this. And the concentration of barium hydroxide is 0.05 originally. And that means that when it all dissociates, the concentration of OH minus will be 0.1. And then we can say that the H plus concentration is equal to Kw over the OH minus concentration, which is equal to 10 to the minus 14 over 0.1, which is equal to 10 to the minus 13. And to work out pH, I minus log this and I get. However, you could have also subbed this in to the second formula over here, and we get H plus concentration is equal to 10 to the minus 14 divided by 2 times 0.05, which equals 10 to the minus 13. And then once again we can minus log it to work out pH as 13. Now for weak acids, the equilibrium is HA dissociates to H plus and A minus, and the formula is Ka equals the H plus concentration times the A minus concentration all over the acid concentration. And in our calculations we assume two things. Firstly, that the concentration of H plus is equal to the concentration of A minus, and we basically assume that because this is a 1-to-1 ratio. And secondly, we assume that the concentration of HA at equilibrium is equal to the initial concentration of HA. And the reason we assume that is because it's a weak acid, so the equilibrium lies mainly to the left, so the acid barely dissociates. And after these assumptions, Ka simplifies to Ka equals H plus squared over the concentration of HA initially. So for a neutralization reaction, calculate how many moles of excess acid or base is left over. Work out the concentration of leftover acid or base. If it's excess base, use Kw. If it's excess acid, use Ka if it's a weak acid, or pH equals minus log H plus if it's a strong acid. Now to answer these questions, I think an ice table really helps, so I'm just going to draw that out now. And notice how I've done F instead of E. That's because the reaction isn't in equilibrium. So firstly, I need to work out the initial moles. And we know that the reaction is going to occur at a 1-to-2 ratio. So if all of this reacts, then 0.00825 moles of sulfuric acid is going to react. And then our final moles are, now that we have our moles of sulfuric acid, we can work out the concentration of sulfuric acid, which is so we do moles divided by volume, and for the volume we use the total volume, which is 35 centimeters cubed plus 30 centimeters cubed. and I'm going to convert that into decimeters cubed, which is, and that's equal to 0.142. And so the pH is equal to minus log of this concentration times 2, because there's 2 protons, and that gets me 0.55. Now a buffer solution is a solution where the pH does not change significantly if small amounts of acid or alkali are added to it. Acidic buffers are made from a weak acid and a salt of that weak acid. For example, ethanoic acid and sodium ethanoate. And the way the buffers work, well, we have these two reactions going on here. So this is the dissociation of the ethanoic acid, and this is the dissociation of the sodium ethanoate salt. So when we add H+, that's going to react with these ethanoate ions, and that shifts the equilibrium to the left to kind of suck up all of the H+ that we've added. And then if we add OH- to the reaction, that's going to react with the H+, and the H+ concentration is going to decrease, and when that happens, this equilibrium shifts to the right to produce more H+, so that the H+ concentration doesn't change much. Basic buffers are made from a weak base and a salt of that weak base. So for example, we might have ammonia and ammonium chloride, and these are the two reactions that we have that happen within it. So firstly, the ammonia is going to act like a base and collect a H+, and in the other reaction we have ammonium chloride dissociating into NH4+ and Cl-. Now what happens is that when we add H+ into the mixture, that's going to react with the OH-, and so the equilibrium shifts to the right, and this reforms all the OH- that we've lost. And when we add OH-, that's going to react with the NH4+, and equilibrium is going to shift to the left to lose all the OH- that we've just added. For calculating pH of buffer solutions, we assume all the A- comes from the salt. So the Ka expression is equal to now for this question I'm going to draw a similar ice table. So we get and we have 0.005 moles of sodium hydroxide initially, and we can work out the moles of ethanoic acid by doing volume times concentration, and that gets me 0.1 moles. And in a similar way we can work out the moles of sodium ethanoate, which is okay, so when this reaction occurs, all of the sodium hydroxide is going to react, and we get, and then from here we can work out the moles we have after everything reacts. And then from here I can work out the concentration of the acid and the sodium ethanoate, which is and then we can rearrange the Ka expression to work out H+, which is And then we can minus log this H plus concentration to work out pH, which is okay. And one more thing that I just want to add is here we did work out the concentrations for the acid and the salt. However, you could have just subbed in the moles over here because the volumes cancel out. Alright, so for pH graphs, you want to know the rough pHs of everything. So for a strong acid, it's around 0 to 3 pH, whereas a weak acid is around 3 to 6. A strong base is around 11 to 14, and a weak base is around 8 to 11. So if I was to react, for example, a strong acid with a weak base, well, a strong acid is between 0 to 3, so let me just put that somewhere around there. And a weak base is around 8 to 11, so that's somewhere around there. And then I just draw a smooth line between them. And one thing you need to make sure is that the pH of the indicator is on the steep line. This point here is called the equivalence point. And if we call that volume V, then at half V, the HA concentration is equal to the A minus concentration. And so the Ka expression would simplify to H plus. And as a result, pKa is equal to pH. Alright, that's it for A-level physical chemistry. If you enjoyed the video, make sure you like, comment and subscribe, and make sure you check out some of my other videos.